Hi, I'm Dylan Foster, and I'm here to tell you about a new open problem with Akshay and Haipeng about model selection for contextual bandits. So in statistical learning, model selection algorithms allow us to adapt to the complexity of our hypothesis class. So let's say we have a hypothesis class or policy class pi that decomposes as a nested sequence of classes pi1 through pi m. Then what model selection algorithms ensure is that for every little m, our risk relative to the risk of the best policy in pi sub m scales only with the complexity of pi sub m and not with the complexity of the whole policy class pi. So in particular, what this ensures is that if our Bayes policy or the optimal policy lies in the m starth class, then our risk towards the best policy only depends on the complexity of the m starth class and log m star. So in other words, we pay a little penalty log m star to adapt to the complexity of the policy pi star. And what we'd like to understand in this open problem is whether similar guarantees are possible for contextual bandits, which is an online learning setting with partial information. So we're going to focus on adversarial contextual bandits, and the model is as follows. We're going to have a context space script X and an action space script A with K actions. In each round, the adversary is going to select a context XT and a loss LT. The learner is going to see the context and choose an action, and then they'll observe the loss just for the action that they selected. And typically, we're going to be given a policy class pi, and our goal will be to have low regret towards pi. So for any fixed pi, it's well known that the best possible regret in the setting is root kt times log size of pi. So let's have a look and think about what a model selection guarantee for this setting might look like. And for this, it's helpful to step back and think about the full information online learning setting, where we get to see the full loss vector at each round. So in this setting, the optimal regret is just root t log pi, so there's no k because we see the loss of every action. And if we're in this nested setting, it's well known that a variant of exponential weights can get us regret that for every m scales as root t times log size of pi m plus log m. So in other words, we get regret towards all the policy classes pi sub m simultaneously, and all we have to pay to do this is this extra log m factor. So that brings us to the first variant of our open problem, which is to get the analogous rate to contextual bandits. So what we want is that for every m, our regret towards policy class pi m scales as root kt times log size of pi m plus log m. So let's have a look at what's known. So essentially, for general policy classes, we know nothing in terms of positive results. And this is true even if we are willing to be loose in terms of dependence on k or dependence on the number of classes m, and even if we're willing to degrade the dependence on t towards like t to the 2/3 or t to the 3/4. So that'll motivate the weaker variant of our open problem, which is the same as the first one, but with two key differences. So the first difference is that we allow poly k and m and log pi factors. And the second is that we're allowed to have worse dependence on t as long as the exponent on t and log size of pi m sums to 1. The reason why we care about having the exponent sum to 1 is that we want to ensure that our algorithm has sublinear regret whenever log size of pi m is sublinear. And in particular, what this means is that if we can learn pi m when m is fixed in advance, we want our model selection algorithm to be able to learn pi m as well. So let me say a little bit more about what's known. So on the positive side, we had a paper at this last NeurIPS that shows that if you're in the stochastic setting and you have a nested sequence of linear classes, then you can get a guarantee of this type with alpha equals 2/3. But it seems unlikely that the techniques from this paper will extend towards general policy classes. And on the negative side, we don't have much in terms of negative results for CBs, but for vanilla multi-armed bandits, it's known that analogous questions are not possible. So it's like not possible to get adaptivity to like the size of the action set. So let me conclude by saying you should solve our open problem because we'll give you $300. But beyond this, we think it's pretty interesting and it's related to some other open questions. So first of all, if you can solve the strong version of our open problem positively, this will essentially get you the best possible regret you could hope for switching regret and in multi-armed bandits and contextual bandits, and it'll improve the state of the art. And on the negative side, if you can show that our open problem is impossible, this will also refute a slightly strengthened version of a Colt 2016 open problem by Joa Freund about second-order regret bounds in online learning. So if this is interesting to you, check out the paper for more details. Thanks.